work and energy can be applied to rigid bodies just like it can be applied to a system of particles. So, original work and energy equation, we have kinetic energy at 1 plus potential energy at 1 plus work from 1 to 2 equals kinetic energy at 2 plus potential energy at 2. This is the same as saying energy at 1 plus work from 1 to 2 equals energy. Now the work for linear, we learn that the work by a force equals the integral of the force dotted with the distance. Work as a scalar, force and the distance are vectors, and so their dot product becomes a scalar. Now, for the work of a moment, if there's torque, then we have the work by the moment equals integral of torque dotted with d theta. That's from theta 1 to theta 2. This one is S1 to S2. So this will come out to be, if force is constant, then we'll have work by force equals force times the distance, or angular, work by a moment equals torque times the angle, or theta 2 minus theta initial, whatever angle you turn through to get from where you were to where you are now. Now, internal forces do no work. Okay, it's only external forces. And then the works add as scalars. So something like that would be in the lawnmower problem. So we have the lawnmower. We said, okay, there's going to be some torque from the motor, and then the person was pushing on it. And in that example, we had done the self-propel separately from the pushing. But if it's on self-propel and you're also pushing, then it can go even faster. So the work here would be something like torque times theta plus the push times distance. But the angle that these wheels spin, theta, is related to the distance by d equals r theta, which is the distance that the wheel has turned. You know, it's the same as the arc length formula. So in that, we would have work equals torque times theta plus force times r times theta equals torque plus PR times theta. So this just shows that you can add the works together. Now, kinetic energy is going to include translation, ½ mv squared, and rotation, ½ I omega squared. Now, if there's no translation, then V would be 0. If there's no rotation, then omega would be 0. But total kinetic energy would be the translation plus the rotation. So, and you always get this kinetic energy around center of mass or a fixed point. So let's say you have a disk, it's spinning around its center, the fixed point and the mass center are the same spot. So mass center and origin, same spot. Now, if you have something else, like it's actually spinning around this point, it's off center, then this is the mass center. This is the fixed point. So when you're calculating kinetic energy, always do it around either the center of mass or the fixed point. Now, energy also adds as scalars, just like we did for particles, so we can add them. We just have to make sure that we get the signs right. So generally, energy is going to be positive unless it's potential energy that's below the origin, in which case it would be negative. And then work will be positive for conservative work, such as by the pushing force, or negative for friction. Energy is conserved if there are no non-conservative forces. So if the work equals 0, then energy is conserved. And for power, we know for a linear case, power equals force times velocity. For angular, power equals torque times angular velocity. So, and this is in watts, joules per second. So Newton meters per second, or joules per second, energy per unit time. So the interesting thing here, this we can kind of translate it into the gears things. So say we had omega 1, omega 2, R2, R1, then one of the reasons that people will use a gear train is because they want to use a little motor to turn a big load. So they need to make the motor stronger than it would normally be. So they amplify the torque using this gear train. So we remember that V equals R1 omega 1 equals R2 omega 2. And V is constant at the tooth. So this would be V here. So that was for kinematics. We can relate the speeds. Now for kinetics, then we can relate the power is going to be constant. So the power equals torque at 1 times omega at 1 equals torque at 2 times omega at 2. So if you're going to use a little motor, it'll have a little torque and a high speed. And then at the output, you'll get a high torque and a lower speed. So if we want to see what is the output torque going to be, torque input times omega input over omega output equals torque at the output. But also, we don't even know the speeds, but we know the sizes. We can relate them from here, because from the kinematics equation, we know omega 1 over omega 2 equals R2 over R1. We've just rearranged that equation. So here the output torque equals the input torque times R2 over R1. So this is how come if you have a little motor here at 1 and you use a big gear connected to it, then your torque output from the gear is going to be a lot bigger. just the gear will be turning more slowly.